Okay, so welcome to video 6 in our discussion on expectation values of random variables. Okay, so we've shown in the previous video that that the inverse image of any event in our new random variable, which is x plus y, is an event in our abstract probability space. And then we define the probability on the image of our random variable x plus y to be if you take any event, take its inverse image, so you get back into the abstract probability space. So if we look at the picture that we have up here, take any event E, take its inverse image back into the probability space, and define the probability of E, define probability of E to be the probability of the inverse image in here. So probability of x plus y inverse of E. So that's how we can work out what this, and we'd call this something like p bar to distinguish the fact that this is a probability measure on this space and this is the probability measure on this space. Okay, so now what we want to do is establish the second linearity property, which is that the expectation value of x plus y is actually the expectation value of x plus the expectation value of y. Now, that is not, at least to me, that is not an intuitive result at all when you think about it. And the incredible thing is that this holds, this formula holds, this second linearity property holds whether x and y are independent, whether x and y are independent random variables or not. Independent random variables or not. Okay, so let's try and get the intuition for why this is true. Okay, so remember what the definition of the expectation value is. The expectation value of some random variable x is equal to the sum over all values that x can take of that value of x times the probability mass function that x is equal to x. So if we remember our setup, we have some abstract probability space which is being mapped onto by this function x. It's mapping it onto this probability space with outcomes in the real numbers. What we are then doing is the probability mass function is the probability of take a single outcome here, A, and remember we're working completely with discrete random variables. So you take a single outcome in this set here, in this probability space, you put it in a set by itself, call that an event, and the probability mass function is the probability that that event will happen, that event happens, and of course it's equal to the probability of the inverse image of A. So the probability of x inverse of the set containing A. We might just put A there. Strictly speaking, we should of course put the inverse image of A, the set containing A rather. Okay. Or in fact, actually, no, we shouldn't, because it's a map onto the outcome. So no, just the inverse image of A would do. This is a event, and we know that if this is a random variable, that this is an event in this initial probability space. Okay, so to prove this and to get intuition for why this is true, the easiest way to do it is to rewrite this sum in a new way. Okay, it's easier, in fact, let's get some more paper, it's easier to write it, let's redraw the picture again, I know, I'm sorry. So if we have this map, x, which is mapping us onto the real numbers, and we have some little a here on its own, and here we have all the outcomes, so this is s, and this is the inverse image of a, so this is potentially a set containing more than one outcome. Okay, so in fact, it's actually, if we take, what we're trying to work out, remember, is the sum over all possible values of x times the probability that x is equal to x. Well, it's actually easier to write this as the sum of over all values of s, over all possible outcomes in this initial probability space over here, times x of s, which is, if you take an s here, it will map it potentially onto a, times the probability of S of the set containing the singleton S, which you can do providing this has either finitely many elements or countably infinite many elements, which, if it's being mapped onto a discrete random variable, it will be usual for that to be the case. Obviously, you could have a continuous. You could have an uncountably infinite set here being mapped onto you could have it mapped onto the Bernoulli space, for instance. But this proof will break down. This fact that you can sum over all values of S will break down in that condition. But if this is either finite or countably infinite, then we can do this. We can say we'll sum instead over all values of S, and we'll do this. Okay, so for instance, if you take an S here, then it will be mapped onto this value A, and the probability of S, if you sum in this sum, you will sum over every single possible outcome that is in X inverse of A, and the probability, remember, of the singleton A is in fact going to be equal to the sum of the probability of, so if we view this as the P bar on this space over here, so let's have this space, let's call this space sigma omega bar F bar, and let's call this probability space omega F and P. Then if you take the probability P bar of the set containing the singleton A, which is equal to, of course, the PMF that X is equal to A, then that's equal to the sum of the probability, where we're using this probability measure, of all the single outcomes such that S is an element of X inverse of A. Now, if you look at all the values in here, so let's have, they are countably infinite potentially, so let's, to abstractify this, to generalize it, let's call this A1, let's call this A2, all the way up to A3, and it goes on and on and on. Then we could do this for absolutely every single one of those. The probability that X is equal to AI is equal to the sum, S is an element of X inverse of AI, times the probability of those single outcomes. So basically what we're doing is we're splitting this set up into the sets which are all mapped onto a single A value over here, and we're saying these sets potentially contain more than one outcome. Sum over every single outcome that's in each of these sets the probability of the singleton containing that outcome, and that will be equal to the probability that you get this value AI if the function is a random variable. Okay, then what we can do is we can replace this here with this, and we get that the sum over all values of X times the sum of S is an element of X inverse of AI, probability of S, probability of the singleton containing S rather, and that would be equal to the expectation value. Well, if you sum over all values of X, this forms a partition of the total set. All values of X forms a partition, all these inverse images of every single value of X forms a partition of the set. So basically what you're doing is you're summing over all values of X, and then you're summing over all these inverse images of X, which is effectively equivalent to summing over every single value of the sample space. You'll go over every single value of the sample space somewhere in here, because every value of the sample space will be mapped onto a value in here, and therefore will be summed over when you're dealing with that value X, and then you'll find it in the inverse image of that value. Okay, so in fact, to make notation consistent, I've been rather inconsistent here. I should have made this AI, and then I should have said sum over I is equal to 1, potentially to infinity. If it's finite, then this will just go up to a finite number, but potentially it's countably infinite. But the same is true for countably infinite as is true for finite. Okay, so we can rewrite this as the probability as the sum of S is an element of omega times the probability of the singleton S, and then each of these probabilities will be multiplied by its respective AI. So we just need to take the image of S. So that is the reason that is equivalent to the expectation value of X. Okay, so now what we can do is we can say that the expectation value of X plus Y is equal to the sum S is an element of omega times the probability of that single outcome times x plus y of s. And now this is where everything just becomes beautiful and easy. This is the sum of s is an element of omega, the probability of that singleton set containing s, times x of s plus y of s, because that's the definition of x plus y of s. And then we just split this up into the sum, s is an element of omega, probability of the singleton containing s, times x of s plus the probability of the singleton containing s times y of s. And then we just split this up into the sum, s is an element of omega, and of course you can do this even if you're summing over a countably infinite number of things. This is just basically the limit of the sum is the sum of the limits. Probability of s, and if it's finite then of course it's true, x of s plus the sum, s is an element of omega, probability of the singleton containing s times y of s. Okay, so that is equal, this is equal to e of x, and this is equal to e of y. So that is the proof of linearity, providing that this set has only countably infinite number of things in, has at most a countably infinite number of things in. Now most of the probability spaces we've seen so far have finitely many things in, so this is certainly true for those probability spaces. And in the next video what we'll do is we'll apply this result to find the expectation value of the hypergeometric distribution.